All right. I'm recording, so thank you. Okay. Honestly, this next property that we learn is something that we've used a million times. Maybe that's an exaggeration, but we've used it a bunch of times, and it's just that we don't necessarily see it in its integral form, like in notation form. It's just what we do. So this is a problem. This could have been something that you had to do on your quiz. You find the integral, the area under the curve from for a certain range of values. I don't know why I can't talk. So the first question asks us to find the integral from 0 to 2 of f of x. This is the graph of f of x. It does say that in the instructions. That, just like everything else, is important. I haven't tried to throw you off by giving you a graph of like the antiderivative or something like that. That would be a total different process. But I have the function that I'm integrating. I want the area under the curve. So my first integral is the integral from 0 to 2. So that is just the triangle. And that triangle has an area of 2. Yep. So that integral has a value of 2. Slightly more complicated thing on the between 2 and 4. It is a square with a half circle with radius 1. So when I put the two pieces of that area together, I don't want to separate them for this example. I have the square, which is 4, and a half circle with radius 1 has an area of pi over 2. That's what you, yep, pi over 2. Yep. Yep. So yeah. I'll write that in here, 4 plus pi over 2. So then if you would have done that, like if I had just given you this bottom integral, that's what you would have done. You guys probably also would have put an extra line here. Just why wouldn't you? But you would have found those two separate pieces and added them together. And our integral ends up being 2 plus 4 plus pi over 2, which is just 6 plus pi over 2. You can, if you have two integrals that one stops where the next one starts, that's kind of what's going on here. The first integral stops at 2, and then the next integral picks back up at 2. You can put those together in one integral. That's what this adjacent intervals property is. It's a simple idea, but in symbols, I feel like this one gives people the most grief. So, always, thinking back to the picture, think about what's going on, or just having in your head that when you're integrating, you're finding the area under the curve. This is the area from 0 to 2. This is the area from 2 to 4. And when you put those together, you have the area from 0 to 4. Okay. One of the things, and I'll say this now, it'll come up in a later example, that integrand, the thing that you're integrating, don't know if I've used that word yet, but this function, f of x, the thing that you're integrating needs to be the same in order to do this. Otherwise, if this is f of x and this is 3f of x plus 1, I'm asking you to find the area under one curve and then the area under a different curve. 3f of x plus 1 is something different. So that's really important, a really important piece to this property that I think in the past it hasn't hit me as like something that was important, but then I started seeing the mistakes. So, understand that for this property, a key component of it is you're integrating the exact same thing every time. So if you try to do something like this with two different functions, that's a great way to get a wrong answer. But then we'll see an example at the end where that happens and how we deal with it. A lot of times it's the way I described it. It's like 3f of x plus 1. We can use other properties to get that to just say f of x. So we'll see that when we get there. So this is the adjacent intervals property. We start putting letters in it, and I think the letters just kind of make it tricky. The idea here is we have on our x-axis an A and a B, and somewhere in the middle there's a C. So when we integrate first from A to C, and then from C to B, we're doing the same thing as integrating from A to B. This property goes both ways. So you can take an integral that goes from a to b and split it so that it breaks up in the middle somewhere. And that's what we do with piecewise functions, if you think about it, right? If you have a piecewise function and you have to integrate it, you have to separate that integral where the pieces change. So we've used this property a whole bunch of times. It makes perfect sense when you're looking at it in context, but when it's just thrown at you with integral symbols, that's what throws people off. So in plain words, you can break an interval in the middle and make two integrals added together. I don't know if that's the best plain words I've ever wrote in my life. Okay, yeah. And that's really what it's saying. You know, just break that interval in the middle, and then you get two integrals added together because you're just figuring out, well, what's this area? What's this area? How much do I have altogether? Cool. Okay. This example 6 is another thing we've done before. Every time we've integrated a polynomial or just anything with a plus or minus in it, we've just treated each of those things separately. We'll take a quick look at Riemann sums to kind of justify this, just to see what's going on behind the scenes, why we're allowed to do this. So I asked to use a left Riemann sum to estimate f of x, g of x, and then we will put those two things together. So we're going from 0 to 6 of f of x. All of our intervals are the same. They're all 2. Don't forget, you've got to multiply by that interval. So the most common mistake on the Riemann sums on the quiz was forgetting about the interval width. So left sum, so we're going to pick the left value of the function, integrating f of x from 0 to 6, using this table, making an estimate, all the words in random order, would be 1 times 2 plus 3 times 2 plus negative 1 times 2. So the function values represent the height of a rectangle. The interval represents the width of that rectangle. Each one of those multiplications represents base times height. I honestly, for this example, don't even care what that adds up to. And since that's just a bunch of numbers being added and subtracted, if this were an FRQ, that answer stands as good, oddly enough. Like, that is the answer to that question if it's an FRQ. You can leave it like that. We'll do the same. You can also add it up too. I'm not saying you have to do that, but we'll leave it like that because it's really more about seeing what's going on behind the scenes. So now I'm going to do the same thing with g of x. So I'm just going to replace the 1, the 3, and the negative 1 with the 2, 4, and 8 from the table. All right, so we'll get 2 times 2 plus 4 times 2 plus 8 times 2. Agree? Yeah. Oops. Look at this. None of my integrals have dx's here. That's terrible. How could I? Horrible. Okay, so let's take a look at f of x plus g of x. So I want to treat this like the function f of x plus g of x, which would be the two numbers added together. So if I was treating it, just that way, I would be adding up the two values of f of x and g of x and then multiplying by 2. So one way to write this Riemann sum is to do directly, which would be 3 times 2 plus 7 times 2 plus another 7 times 2. But where did those come from? The 3 came from 1 plus 2 times 2. And the 7 came from 3 plus 4 times 2. And the other 7 came from negative 1 plus 8 times 2. Which, if I choose, I'll do it this way, I'll color code it. I'm just going to separate this addition out. In the end, this is just a really big, long addition problem. And every single number in the like double parentheses, the parentheses with the plus sign in it, is being multiplied by 2. So I'll start with the blue numbers first. I'll just put 1 times 2 plus 3 times 2 plus negative 1 times 2. I'll make another color here. We'll do red. It's thick red, but that's okay for now. Just use always drives me nuts that that's big. Fix my issue right now. 4 is good enough. All right, and now I'll do the red one. So plus 2 times 2 plus 4 times 2 plus 8 times 2. And if you look at what I have in blue and red, isn't blue just the first integral? Yep. And isn't red just the second integral? Yeah. So this is the integral from 0 to 6 of f of x dx plus the integral from 0 to 6 of g of x dx. So that's kind of a sketch of like the proof that you're allowed to break up an integral by addition and subtraction. It's not the full thing because I did it with a Riemann sum rather than using like limit notation, which just would be a lot uglier. You can just see how the pieces fall together. Each of those things that I wrote after this bottom integral are equivalent. I showed you where I got the 3, 7, and 7, and then it's really just a long string of things being added. So I just switch the order of those around. So that's why we're allowed to add and subtract. So the integral from a to b of f of x plus g of x is just the integral from a to b of f of x dx plus the integral from a to b of g of x dx. And again, in plain words, you can treat a sum or difference as 2 separate integrals. Much like derivatives, the stuff you can do is easy. I think when you look at, what you actually are doing, it's like, oh, I just make it 2 separate integrals, or oh, I just take we did this one 2 days ago. We could just take a constant multiple outside of the integral. That's not the hard part. The hard part is knowing what you can do and knowing what you cannot do. And if it's not one of the things in these properties that we've looked at, according to this, it says property 6, but who knows whether I got that numbering right. So if it's not one of these 6, or hopefully it's 6 properties, it's probably something you can't do. This goes back to how many times did I say, yeah, but you have to do the product rule here when you take a derivative. You can't just do what you did. Oh, you have to take a quotient rule when you do that derivative. You can't just do what you did. And it's the same things work, I think. What works with derivatives works with integrals. So looking at my bottom example, which I know I said on Monday as well, but I think it's important enough to say it again, this is not one of the properties that we wrote, right? I mean, it actually is a property because it does not equal. You are not allowed to do this. This will get you the wrong answer. I have an odd switch of limits there, but they shouldn't be in the same order. This is not one of our properties. We cannot just break up the multiplication. That means we can't break up division either. We can't just do something weird with an exponent. Only the properties that work. And as a matter of fact, a lot of times these are even more complicated. It's not just like there is a product rule here. There's no product rule for integrals. There's no quotient rule. We're going to look at a couple specific quotients that we can figure out in the next unit, but we're never going to have just one go-to procedure for quotients. And that's really because we're reversing a rather complicated process when we integrate. So that's just how it is. I've given you the warning. Let's do a couple examples of using these properties. So this is a common type of AP question. It's not like there's going to be 50 of them, but it's a really good multiple choice question. In the given information, they are going to tell you some integral values. So if I integrate the function f from 0 to 3, I get 4. If I integrate it from 3 to 5, I get -6. So it's giving us just some information, and then they're going to ask us to basically just use some properties. And notice it says calculate the following integrals if possible. On some of these, we're going to say, yeah, no, we can't do that. All right. So let's take a look. The first thing we want to do, letter A, is integrate from 0 to 5 f of x dx. Obviously, I'm only going to use the f of x things there. What do I do with that information for f of x? Just add them, right? 0 to 3 and then 3 to 5. The area under the curve from 0 to 3 is 4. The area under the curve from 3 to 5 is -6. So this is 4 minus 6. We took the area from 0 to 3 and added the inner area from 3 to 5. And 4 minus 6 is -2. Honestly, they're most often, I mean, on my quick tests, please, just because I want to see where you got your answer from. If you don't, I'm probably not going to kill you. This is multiple choice. This isn't FRQ stuff. But I mean, it's FRQ. The idea is I would never ask me. I would say yes. If I know what to write, I should write it, especially if it's that short and simple. How about letter B, the integral from 5 to 0 of g of x dx? That is -2. If you switch those limits, you get -2. Letter C, the integral from 0 to 5. Yeah, like that one I wouldn't show. Like they're just to kind of re-answer Nate's question on that one. My gosh, showing work on that one I wouldn't. It's just I saw that the limits were switched, so I'm just putting -2 as my answer. That's supposed to be an equal sign, but I don't know what I'm doing. There we go. Cool. Right. Letter C, integral from 0 to 5 f of x plus g of x. Another easy one. No. Yeah. No. From 0 to 5 of f of x g of x, I need to add the integral from 0 to 5 of f of x dx. Yep. Oh, you know what? You're right. Sorry, guys. I was looking at this one thinking that was the number we needed. That's why I was saying no to. Oh, you guys were right. Plus 2. Boom. Yes, correct answer 0. Yep. So I think all three of those are straightforward. I gave a good example of how you can make a simple mistake on purpose. Of course. I said I don't want to pull that off. Letter D. G of x, yeah. -10, yeah. Because this sort of comes from the fact that I don't have the answer, but I know that the total area from 0 to 5 is 2. The area from 0 to 3 of g of x plus the area in question, which is 3 of 5 g of x, has to equal the integral from 0 to 5 g of x dx. So we end up with 12 plus what equals 2, and that answer is -10. Cool. So you can see that property can come in a couple different ways. Letter E. I like it. Who said it? You cannot do it. That is a quotient. Nope. What's wrong with the next one? I have subtraction and I have constant multiple. I have a property for addition and subtraction. I know I only wrote it as addition, but I mean, that is addition. It's plus -4 g of x at the heart of it. So that follows the addition problem. Do I have a constant multiple property? You gotta think all the way back to Monday, but yes, just like derivatives, integrals have that same constant multiple property. So this is the integral from 0 to 5 of f of x dx minus 4 times the integral from 0 to 5 g of x dx. So it looks like we have -2 minus 4 times 2. -10 sound right? I think the next two examples are good ones because they're conceptual. You have to understand what's going on. Letter G says evaluate an integral and then take its absolute value. Is there ever going to be a time where I say and then take its absolute value where that's not going to work? No, right? Yeah, that's fine. This is totally doable. The integral from 0 to 5, the absolute value of an integral is just the positive version of that integral. So we've already solved this one. This is the absolute value of -2. So 2. Letter H says integrate a function that you've taken the absolute value of. We know that, and I, for some reason, switched the order of the limits. I haven't looked at this since last year, since I started teaching of it. That part doesn't matter. I guess we know that, I'm just going to fix them back so that I feel like I just adds a layer of me explaining things that I don't need to. I'm just changing the problem from scratch. Pretend that was the problem on your paper. Yeah, no, I agree with you, but I'm saying I'm not making the same problem. I don't like the fact that I have those backwards because it's a layer of things that I need to explain. But no, flip. So that's the problem. That was printed on your sheet. Pretend it was. But now here's the thing. We know that this integral without the absolute values is -2, but we don't know where that -2 came from. Maybe it was a purely positive function and we found out that this area was 2, right? But maybe this function was something like this, where we actually found out that the area here was 4 and the area here was -2. We have no idea. If I just tell you that an integral equals 2, that might mean that there are 2 positive units of area between 0 and 5, but it might mean that there are more than 2 positive area units of 5 that are then subtracted from with negative things. When I find the absolute value of a function, what that does to the graph is it takes anything that was negative and it reflects it up over the x-axis. So my orange is the graph of f of x. The absolute value of f of x is this. The absolute value of f of x here is this. So if I integrated that function after I took its absolute value, on the left, I'd get 2. On the right, I'd get 6. So you cannot do it. Without more information, I cannot do letter H. If I had the function itself, maybe now there's something I can do, but right now I'm at a cannot determine. And last but not least, something we haven't talked about. This will be our main type of integral that we'll spend like a good 3 days on in a couple sections. F of g of x. Could I just do something simple when I took a derivative of f of g of x? I could not, right? Because this was chain rule. This is the chain rule. That means that I cannot do something simple here when I integrate. So this is another cannot determine. Yes, this is U substitution. So sums and differences, constant multiples, those are the things that we know how to do. All right. And then last but not least, this was the example that I started off talking about. This is one where we're going to have, I believe, adjacent limits. We are going to go from, and some of them are backwards. I feel like this one throws the whole kitchen sink at us. We have an overall interval of -5 to 5. And then we have 2 integrals where it's broken up at -3. Those are both upper limits, but any of these can be switched by just making the result negative. But this isn't as simple as doing something like -4 minus 10 or -4 plus 10 or some sort of combination of -4 and 10, because here the function is 3f of x minus 4. here the function is f of x, and here the function is 2f of x. So before we can start using limit properties, we've got to get any of these things. I guess this one is still on question mark, so we'll put that part on hold for a minute. But we want to get this thing to say what -5 to 5 of f of x is. Okay, so that's going to be our first goal here, is to get this translated into something that says -5 to 5 of just plain old f of x equals a number. So let's see how to do that. We'll use our integral properties. This -10 is also equal to 3 times the integral from -5 to 5 of f of x minus 4 dx. But that is also equal to 3 times the integral from -5 to 5 of f of x minus the integral from -5 to 5 of 4 dx. Thank you. Yell at me every time I do that, because I'll yell at you every time you do it. So we'll be consistent. I don't know. No. You are one of a million. You've done that, the same mistake that one of a million people have done. It is not -4. It is minus the integral from -5 to 5 of the constant function 4 dx. That actually is its own integral, its own property. You can do this one of two ways. You can do the power rule here. This is 4x evaluated from -5 to +5. But this is also a rectangle with height of 4 and width of 10. So the integral from -5 to 5 of the constant function 4 is equal to 40. The integral is equal to 40, but I'm going to write minus because there's a minus in the problem 40. Yep, good question. Yes. The integral itself is 40, but it has a minus sign in front of it. And we're going to say that this thing equals 10. And now we're going to be where we want to be. Oh, minus 10, right? Good. I was going to say that was going to come out to something that didn't divide out well. Okay. All right. So that means that 3 times our integral equals I isolated that integral, so I need to solve and get 30. Add 40 to both sides, right? Sorry, I thought. Yep. Just from an add 40 to both sides. We are solving for the integral. So that is algebra 1 solving for the x, except instead of x, we have this integral, which means that our integral equals 10. Divide both sides by 3. Yep. It's algebra 1, except your nice friendly x from algebra 1 is replaced with a big ugly integral. Right? Jack takes offense to me calling an integral ugly. It's elegant. That was the word he used yesterday. Yes. Yeah. Okay. So we now know that the full area of just the function itself, f of x, is 10. So we can use probably an adjacent situation here. We need to know -5 to 3, so we can write the integral that we have, which is -5 to 5 of f of x dx, is equal to, from -5 to -3, which is almost what we need, plus the integral from -3, start back up where you stopped, to 5 of f of x dx. Whenever you write this out, you want to make sure that your stopping point is the next starting point, regardless of what happened up here, because now we can fill all these in. We said that this is 10. Thank you. Call me out every time. You'll remember it better if you keep calling me out on it too, I think. 10 equals the thing that we almost need plus what goes in that last spot? What is the integral from -3 to 5 of our function? It's +4, right? Again, because we were given that information, but we were given it with the limits switched. So almost our answer, the integral from 3, not a pen. The integral from -5 to 3 of f of x dx equals 6. So the integral of twice that function is 12. And again, that's using the constant multiple property. I'm just pulling the 2 out front, which you are allowed to do. I think I took and found when I made this problem, I found like every possible thing they could do to you and stuck it all in one problem. Sometimes there's like 1 or 2 less properties that you have to use along the way, but this is the idea. The thing is, you've got to back out anything that's more complicated than just f of x and get it solved for f of x. Do not make the mistake that I've seen a million times in my 2 years teaching this class of, it's an integral of a constant. Let's just recycle that number. This thing is just 4. No, you've got to either use the fundamental theorem for x evaluated at the 2 numbers, or remember that that's just a rectangle. So it is the number that's the integrand, because that's the height, times the width of the interval, because that is the width of that rectangle. What's that? Which 3s? There's lots of 3s. Yes, they are supposed to be 3. Thank you. Yep. I mean, that's great. Like I just showed you like, whoa, here's this problem. Like this is one you have to practice. Like you have to kind of go through the process of figuring out, okay, what's next? Okay, what's next? But you have to, that's your thought process you need behind your head. You need to get yourself down to just f of x as the integrand, as the thing that's being integrated. Use properties to do that. It's going to look something like this, a number, an x. There could even have been like an x squared here, which would have been fine. It just would have made, you would have forced your hand to do fundamental theorem in this step. So there could be just algebra or any of our functions in there. Cool. All right. Not bad. You still have, almost 20 minutes. No, more than 20 minutes. About 20 minutes.